In this podcast, we're going to take a look at acid-base equilibrium, just like the equilibrium we've been doing. In the past we've talked about strong and weak acids and bases. And strong completely ionize, but weak, we've talked about weak as only partial ionization, but we can look at Ka, which is the dissociation for acids, and Kb, the dissociation for bases. And actually it's going to be a two-headed arrow because they're only going to partially ionize. Okay. So as I'm sure you know, acids are involved in, are found in a lot of things that we eat, specifically fruits. Bases are involved in a lot of things that we find at our homes, mostly a lot of cleaning products, but also things like antacids, Maalox and Tums and stuff like that. Bases have a sour taste. They will react with metals, which is why we have to be careful putting acid down the drain because it will eat up the metal in the pipes. And of course they neutralize bases. Bases taste better. Think of soap. Soaps are basic in nature. They are slippery, just like a soap would be slippery, and they do not neutralize acids. Alright, so if we look at these four acids here, we have two that are considered to be binary because they only come from two elements. And remember, it's hydrofluoric. If it's binary, it starts with the hydro and ends with ic, right? So hydrofluoric, hydrobromic. And then we have two acids known as oxyacids, and these come from the polyatomic ions. And remember, I ate something icky. So if I have an 8 ion, like a nitrate ion, it becomes nitric acid. There's no hydro on that. If it was a us's, become ites, okay? Or ites become us's, I should say. So nitrite becomes nitrous acid, okay? Remember that? Okay. The thing that's common, though, between all of them is that they all lose an H plus when in water, and that's a definition of an acid. So we're actually going to talk about two definitions. One is the Arrhenius definition, and then we'll talk a little bit about the Bronsted-Lowry definition. The definition of an acid for Arrhenius is that it produces an H plus in aqueous solutions, and you can see that happening here. It goes from a H plus and an anion, and it forms H pluses in solution. Okay, and we do use a big arrow here going to the right because it is completely ionized. Hydrobromic acid is a strong acid, completely dissociates. So even though we say we get an H3O, we get an H plus here, we're really get an H3O plus. We just sort of shorthand it by saying we have an H plus, but we in fact form hydronium ions. So we consider those to be the same. If you think about a hydrogen atom is one electron and one proton. So when it becomes an ion and loses its electron, all we have left is a proton, which is why we often will call H plus a proton. Our definition of a Bronsted-Lowry base is that it produces hydroxide ions in solution. Okay. So just talking a little bit about strong versus weak, you do need to memorize the strong acids. Hydrochloric acid is a strong acid, so we show an arrow all the way to the right because it will completely dissociate. And something like a weak acid, like acetic acid, would have a double-headed arrow because it's only going to partially ionize. And in fact, the equilibrium will lie to the left, whereas the strong acid, it's all the way to the right. Okay, so let's talk a little bit about a Bronsted-Lowry acid. So a Bronsted-Lowry acid are conjugate acid-base pairs that differ by one hydrogen, and an acid is considered a proton donor. And you can look here, we have this water that donates a proton to this base, which is NH3. And a base is considered to be something that accepts a proton. So in this case, the ammonia is acting as the base, accepting it. And we form these conjugate acid-base pairs. So when the water donates its H plus, the ammonia, the ammonia picks it up, becomes the ammonium ion, which allows the new substance, the ammonium, to act as an acid because now it has an H plus that it can donate. So this acid, this base, and this acid exists as what we call conjugates, and they differ by only one hydrogen. Okay. All right. So the conjugate acid donates again to the base, and we form conjugates again. Water is considered to be amphoteric, which means it can act as both an acid and a base. Here we see a water, and you could imagine that this hydrogen is being donated to this water, and in the process of doing it, this water is considered to be the acid, and this water would be considered to be the base, and we end up with H3O plus and an OH minus.